Japan. His interests are in computer security, networking, operating system, virtualization, trusted computing, digital forensics, and intrusion detection. He published a lot of academic papers in those fields and frequently gets around the world to present his research results in various hacking conferences. Nguyen obtained his PhD degree in computer science from Keio University, Japan. He's also a member of Nguyen Security, a pioneer security research group in Vietnam.
So let's start now. Okay. So today I'm going to give a talk about eKimono, a malware scanner for virtual machine. Okay, so my name is Nguyen, and you just call me Quyuh, which comes as last in my name, and I'm working in Japan now. So here's what I'm going to introduce today. At first, I'm going to introduce the problems of current malware scanner, and you can see that there are many problems that cannot be fixed with the current design. And after that, to fix those problems, I introduce a new malware scanner that works for virtual machine, which can be used to detect malware running inside virtual machine. So first, I will briefly introduce virtual machine concept, and after that, I introduce the architecture, design, and implementation of eKimono. And because I don't have much time, so in this talk I focus more on Windows protection, and I focus more on detecting rootkit running inside Windows virtual machine. And after that, I have some live demo for you, so you can see that eKimono can really detect some real rootkit running inside virtual machine. And after that, conclusion. So the first part, I introduce the problem of current malware scanner with a rootkit. First, what is rootkit? I think everybody here knows what rootkit is. Rootkit is type malware that's trying to hide the existence in the system, so you don't know that your machine is infected with the malware. So the rootkit can come in the shape of a Trojan. So the rootkit can install Trojan in your system, and the Trojan can replace the system binary, so it returns the fake information to you. And the other type rootkit, which is more dangerous and it's harder to detect, is the kind of rootkit that try to modify the system to hook critical function that can disclose the rootkit in the system. So first of all, the rootkit can try to patch the system process at runtime. They can try to patch import arrest table, export arrest table. They can try to do inline hooking, or they can even modify the system kernel. So they can patch the system code. They can change the import the interrupt descriptor table. They can change the ZDT. They can modify the import arrest table, export arrest table, and they can also modify kernel objects using, for example, the decomp technique. So you can see that there are a lot of techniques can be used by rootkit to hide the existence in the system. Okay, so to detect rootkit, what to do? Of course, usually you run some malware scanner to detect the malware in your system. So the idea is that to detect the malware inside your system, you run the malware scanner inside the system. And remember that mostly the current malware scanner only scan hard disk to detect malware. So yeah, you can see that there are many problems with the current malware scanner. First of all, you can see the malware can run inside user space, the malware can run in the kernel space, and the malware scanner can run in user space or kernel space or both. And you can see that there are some big problems. So first, because first of all, you can have the malware running inside the kernel, so the malware can return the fake information to the malware scanner. So the malware scanner cannot see the real information, right? So that means the malware scanner can be easily fooled by the rootkit, especially if the rootkit runs inside the kernel. And because if the rootkit runs inside the kernel, it can easily tamper with the rootkit scanner, with your malware scanner, and you can even attack your malware scanner. It make it work incorrectly, or it can even kill your malware scanner, for example. So the malware scanner doesn't work correctly anymore. The other problems. So as I said in the last line, the current malware scanner mostly focus on scanning the hard disk, but most of them ignore the memory. They don't scan memory, but they focus on scanning the hard disk only. So recently there are many advanced malware that they try to evade the malware scanner by staying inside memory only, but they never write down themselves to the hard disk. So you can see that for those malware that only stay in the memory, the malware scanner that only focus on the hard disk cannot detect them because they don't scan the memory, but only the hard disk. Those are the other problems. So you can see that some problems cannot fix by the design. So we have a dream. I want to have a perfect malware scanner. So I have 3 requirements for my good malware scanner. So I want a malware scanner that can detect the malware inside the memory, not only in the hard disk. And the second, my malware scanner cannot be easily fooled by the malware, even if the malware running inside the kernel. And finally, it cannot be very hard to be tamper attacked by the malware, even if the malware running inside the kernel. And you can easily see that those requirements, the last 2 requirements, cannot be fixed in the current design, because the malware running inside the same system as the malware. Okay, that is the first part. The second part, to fix the problem, I introduced a malware scanner named eKimono that focus on scanning the rootkit inside the virtual machine. So what's the virtual machine? I think everybody here know virtual machine very well, right? So basically, virtual machine allow you to run multiple virtual systems on the same physical machine at the same time. And first of all, on the screen, you can see that at the bottom, we have a thin layer named virtual machine monitor or hypervisor. And on top of that, I run 3 operating systems at the same time. And in the virtual machine concept, they actually classify virtual machine into 2 types, a privileged virtual machine and guest virtual machine. So the idea is that from the privileged virtual machine, which is also called host virtual machine, you control all the other guest virtual machine. So first of all, on the screen, you can see that the host virtual machine is the green one. And from the green virtual machine, from the host virtual machine, the green virtual machine, you control the other 2 guest virtual machine. How about Zen? Zen is an open source virtual machine that come in ZPN license and is supported in Linux kernel now. And in Zen, they call the host virtual machine domain 0, and the other guest virtual machine are called domain U. And from domain 0, you control other domain U. That's about Zen. How about QEMU? QEMU is another type of virtual machine. But you can see that in QEMU case, you run the guest virtual machine inside the QEMU process, and QEMU process run inside the host operating system. It's similar in KVM case. KVM virtual machine actually use QEMU a lot, and a guest virtual machine actually also run inside QEMU process. But you can see that we have one layer of software named KVM, which allow you to run a lot of code on the physical CPU, not on virtualized anymore. And KVM actually use a CPU that support virtualization like VTX from Intel. Yeah, you can see that KVM is much faster than QEMU because they have hardware support. So to control a lot of different virtual machines like this, people come up with a framework named libvirt, which is open source and supported by many organizations, many companies in industry. And libvirt provides a framework. So using libvirt, you can access to own kind virtual machine. And actually, libvirt is virtual machine independent. And so far, libvirt supports Zen, KVM, QEMU, VirtualBox, VMware. And inside libvirt, they also include a toolkit to manage the own kind virtual machine. So you can see that recently, libvirt become a de facto method to manage the virtual machine, which is included in many Linux distribution now. So you can see that on the screen. libvirt is kind of a framework, and libvirt can be used to manage many kind of virtual machine, Zen, KVM, QEMU, VirtualBox, VMware, and on top of libvirt, you can build your application, which use libvirt to access to and to manage all those virtual machines. Okay, so how about detecting malware for virtual machine now? The idea is that we design eKimono, the malware scanner for virtual machine, by putting the scanner outside of the protected virtual machine. And actually, we put the scanner inside the host virtual machine. And from here, we let the scanner access to the rest virtual machine memory, and we perform many actions. First of all, you can scan the memory of the rest virtual machine to detect malware. Or you can even manipulate the memory of the virtual machine. So first of all, you can disable malware if you want to. And here's the architecture. It's very easy to understand. You can see that in the host virtual machine, I run the malware scanner. And from here, the malware scanner access to the memory of the rest virtual machine. And we can scan the memory to detect malware inside the rest virtual machine. And because we can do that because all the virtual machine allow you to access from the host virtual machine to rest virtual machine, because they usually provide some virtual machine interface, and you can use that interface to access to the memory of the rest virtual machine from the host virtual machine. So we can see that with this design, my dream come true. You can see that this can delete the memory resident only malware, right? I delete the malware that stay in the memory. And from outside, I can get the correct information even if the malware run in the operating system of the virtual machine. Why? Because I don't rely on the virtual machine operating system to get the information. I can show you how to do that later. And because my scanner run outside, so the malware inside cannot attack it, right? It cannot tamper with my scanner. It cannot attack my scanner. And this one is impossible by design. And besides those advantages, we have some more advantages. First of all, my malware scanner is invisible to the malware. It runs outside. The malware inside cannot know that it is being monitored by the scanner running outside. And from outside, you can effectively disable the malware by manipulating the memory of the virtual machine, of the guest virtual machine. Yeah, the idea is very nice, easy to understand, and sound very simple, but actually it's not. There are many challenges to develop such kind of malware scanner. First one, because from outside you want to understand the virtual machine, the memory of the virtual machine, but usually from outside you only see the raw memory. From outside your scanner only sees the first page of the memory, second page physical memory, third page physical memory, and that's all. There's no context from the memory. You only see the physical memory. So you have to analyze the raw memory. You have to analyze the physical memory to understand the internal context from the memory that you can access to from outside. And because from inside, first of all, you want to locate and you want to access to many system object inside the memory. First of all, you want to access to the memory that contains the kernel module. You want to access to the memory that contains the process and many things like that. But all those things are represented in the virtual memory, not in physical memory. And from outside, you only see the physical memory. So the first challenge is that you have to understand the virtual memory. And you know that you only have access to physical memory. And the second part, after you can understand the virtual memory, you have to access to the virtual memory, and you have to get the OS semantics object from the virtual memory of the virtual machine. And of course, this part you need to have very good understanding on the operating system of the virtual machine. So there are two problems: how to understand the virtual memory and how to get the OS semantics object from the virtual memory of the virtual machine. And we solve those problems by designing a multiple layer framework. To understand the virtual memory, we design the framework named AnyDoor. To get the OS semantic objects from the memory of the virtual machine, we come up with another framework named eKimono. And here is the full architecture. We split the eKimono into multiple layers, as you can see in the screen. At the bottom, we have framework named AnyDoor. And on top of AnyDoor, we have another framework named eKimono. And on top of that, we build many applications that access to the guest virtual memory to perform many things. And eKimono can be used to scan the malware inside the virtual machine. So after this, I will go into detail of each layer in this picture. The first layer, AnyDoor. As you will remember, AnyDoor can be used to access to the physical memory and virtual memory of the virtual machine. And you can see that we build to support all kind of virtual machine available. We build very flexible design, and each virtual we design a kind of interface it's kind of a plugin interface, and each virtual machine can be supported as a plugin. So you can see that we provide a plugin interface for all kind of virtual machine, and first of all, to support Zen virtual machine, you have plugin for Zen. To support virtual machine which is supported by libvirt, we have a libvirt interface, and to support virtual machine from VMware, we have a VMware interface, VMware plugin. And you can see that in this framework, the middle layer is here to convert from the virtual memory to physical memory, and after that, it is a below plugin to access to the physical memory. And actually, AnyDoor is designed to work with all kind of operating system, but we still want to take the advantage of some knowledge we know about some specific OS to speed up the converting process from virtual OS to physical OS. So we should have some optimization and enhancement for some particular OS like Linux and Windows. Okay, so here I emphasize again. AnyDoor can access to physical memory of the virtual machine, and it doesn't depend on operating system, and it works with all kind of virtual machine, and actually it supports Zen, KVM, and QEMU out of the box so far. You don't need to do anything to support those virtual machines. And we can also support VMware, but not yet, and I explain later why. And AnyDoor gives you access to virtual memory, and actually it plays a kind of role of memory management unit, as in the MMU unit in the physical system, and it's kind of software-based MMU to convert from virtual OS to physical OS, and it understands all kind of memory mode available in Intel architecture now. And this framework also provides access to the register of the virtual machine. Yeah, AnyDoor supports Zen now, and we re-implement some code from Zen for the Zen VM plugin, and the Zen VM plugin can access to the virtual memory and physical memory and register the guest OS, and the reason I re-implement the function from Zen to accept to those things, because I don't like the original license from Zen. It's in ZPN. So I re-implemented them so I can release them under NZPN license. To support libvirt, Yeah, Liver's nice because actually it actually provides some access to the virtual memory. So actually you don't need to convert from virtual memory to access to physical memory to access the memory in virtual machine supported by Liver. So we take advantage of the virtual memory access already available in Liver to speed up the access to virtual memory. But anyway, we still need access to the physical memory of Liver. And originally, Liver doesn't support accessing to physical memory. And to support the access to physical memory, I need to develop a patch for Liver. And I submitted a patch to Liver project, and it was accepted from the last August. And the patch, the physical memory access to Liver is already available from the Liver version 0.7. And you can see the patch supported by me here. It allows you the access to the physical memory of the virtual machine in Liver. How about VMware? I think many people need to ask that because VMware is very important and very popular. And VMware is actually trivial to support because you only need the access to the physical memory of the virtual machine, and actually that functionality is already provided by the VM-Shape API from VMware. But unfortunately, the VM-Shape API is not open to the public, so we cannot support VMware so far. But once they release the VM-Shape API to the public, we can support VMware very easily. And there's some simple for the AnyDoor framework, so you can see how it works. There's some API. So you can see the two top function, AnyDoor read user and AnyDoor write user. Those functions can be used to access to the memory of the process inside the virtual machine. You can see that you just need to provide the page table, the OS, the virtual memory OS. That means which OS you want to access to, and the buffer you want to keep the memory, read or write, and how many bytes you want to read and write. And the last two functions, you can see that you can use them to read and write to the physical memory in the virtual machine. You can see that all those functions they don't depend on the operating system. It works with own kind of operating system. Yeah, that's the first challenge, how to understand the virtual memory, and we solve that by a framework named AnyDoor. The second challenge, how to get the OS semantic object from inside the virtual memory of the virtual machine. And to solve this problem, we have another framework named eKimono. And eKimono is a framework that runs on top of AnyDoor. And eKimono uses a service provided by AnyDoor to access to the virtual memory and physical memory of the virtual machine. And eKimono can be used to get the OS objects from the virtual memory and physical memory of the guest virtual machine. And because we want to use eKimono for security purpose, so eKimono focus on important objects, especially which is usually exploited by malware or can disclose their residence inside the memory. So we focus on objects like network port, network connection, process, kernel module, and so on. And here is the architecture. We also split the eKimono framework into multiple layers, so it's very flexible and can be easily extended in the future. And now I am going to explain what each layer does. Why I split eKimono framework into multiple layers like that? Because there are many challenges. First, now you can, thanks to the AnyDoor framework run below the eKimono framework, you can access to the virtual memory and physical memory. So now we want to get the semantic object from the memory, right? So you need to have very good understanding on the OS internal. So actually this framework really depends on the OS, on the particular OS. At first, you need to locate object in the memory. For example, you want to get the list of all the kernel module loaded inside the virtual machine. So we want to locate all the object that contains the kernel, the information on the kernel module, right? And after that, after you can locate those objects, you need to get information from inside each object. So now, for example, even I focus on those things like kernel module, processes, thread, system handle, open file, resist G, DNN, network connection, network port driver, and so on. And we need to locate those objects inside the memory. And actually, in this part, I don't invent anything new. I rely on the research done by the community. There are already a lot of research done about how to locating those objects inside the memory, and I don't really do anything new here. Okay, so after you can locate those objects, you need to get information from each object. For example, you know that in Windows, the object keep information about each process is named _ eProcess, like that. And now, after you can locate the object contained on eProcess, on eProcess structure, you want to get all those members inside that structure out. For example, you want to know when the process was created. You want to get the create time member from that structure, right? And to get the create time member from that structure, you want to know that this member create time stay at the offset 70x, and it has a size 8 byte, right? So to get in all the member from each structure, you want to know the offset of each member. But the problem is that you must understand very well about all the structure inside the operating system. And for example, in Windows, there's another problem. Those structure can change between Windows version. So with each version of Windows, they can move some particular member field around. They can move it around, or they can even switch their position, or they can add a new member, or they can do many things. And you can see that the offset really changes between Windows version, and that's a big problem. So what is the current solution? So there are many many projects that try to locate the objects and get the information from those objects inside the memory, and they deal with the problems by the hard code on the popular objects in their program, and they hard code also the offset and the size of those member fields that they are interested in, and everybody does the same thing. But you can see that that's not good enough. Why? Because this hardcore solution, you can see that the information you can get out from those objects limit on the object you specify in your source code, and it also limit to those members you specify in your source code. If you want to access to the other things that are not available in the source code, you cannot do anything, right? So to get all those information, I have another dream. I want to be able to query the structure of all the objects with all the member field inside. And I want to support all kind of operating system with different versions. And I want to do that on demand at runtime with all kind of objects. And I want to answer many questions. First of all, I want to know what is the size of this object, and what is the offset of this member inside that object, and what is the size of that member inside that object, and so on. There are many questions I want to answer. So to solve that problem, I have another framework named LeadDI. Yeah, we have many frameworks. And LeadDI can satisfy all the above requests, and it makes your dream come true. Actually, it's kind of another framework, and we rely on public information on operating system object. We don't really have access to the internal information from those operating systems like Windows, which is closed. And libdi work with all kind of OS. It supports Windows and Linux very well so far. And the solution is that we build the information about each operating system object in the object file, which come in a debugging format, and we extract all those information from the debugging file at runtime. So here's about Windows. To support Windows, initially I rely on the React OS source code. Anybody here doesn't know React OS? React OS is an open source project that they try to build the open source OS that can run on the Windows application. So the idea is that if you have some Windows application, normally you have to buy Windows OS to run your application, right? So the idea is that if you have React OS, you can run your application, Windows application on React OS, and you don't need to buy Windows OS. That's the idea. And React OS is free and open source. It supports Windows 3000, 2003 and up. And you can see that to get the information from the Windows object, I compile the React OS file header with the debugging information. So you can see in the last slide, I use a GNU compiler, and I build my small program that include all the React OS prototype inside the code, and I compile it with debugging option. And the idea is that with each version of Windows, I have one object file. So there are some problems. Because React OS so far only support Windows 2003 and up, so I need to patch the React OS header so it can support Windows XP and the version other Windows version before that. And I rely on Windows debugging simulator, which is open to the public. And besides that, really React OS, there are many problems in the information. First of all, there are many incorrect information in the React OS source code, so I need to fix the incorrect and not updated data structure from React OS, so we can support Windows Vista and Windows 2008, for example. And for the recent version of Windows, like Windows 7, React OS doesn't support, so I need also to patch React OS prototype header to support Windows 7. And here are some libdi API, so you can see that how we can use it to access to all the information from those objects. First of all, you can see that the top function di structure size. You can use this one to get the structure size if you give this function a structure name. You can also give the size of each member inside the structure if you use the second function di member size, and you need to give this function the structure name and member name. And even to get the offset of a particular member, you call the third function di member offset, and you give this function the structure name and the structure member. Here's a very simple code using libdi. That even to get the information from the Windows XP Service Factory version, I can call the function name di open, and I open that object file for build for Windows XP Service Factory. And the next slide, I can call di structure size to get the size of E process structure. Next one, even to get the member size, the size of member create time inside the E process structure, I call di member size and gives that function the E process and create time as a parameters. And lastly, you can see that I can get the offset of create time using the di member offset function. So it's very easy, and you can do that at runtime with own version of Windows. You can access to all the structure and all the member inside each structure. Okay, so after you can accept, you can have the internal information of all those objects. You can use those information to actually extract those objects from the from the memory for the virtual machine for you. So we design the API, so it's very hard to be abused by the malware running inside guest virtual machine. So we design the API so that you can get the first object in the list object. For example, you want to get the list of all the kernel module inside the virtual machine. You call one function to get the first object, first kernel module, and after that you have another function to get the next kernel module inside the list, and so on. You repeatedly call that function to get the next object until you reach the last object. So here's some simple API from eKimono. For example, you want to get the first process inside in the list of all processes inside the virtual machine. You call the first function get task first, and this one returns the rest of the objects that keep the information about the first process in the memory. And after that, you call the get task next to get the next process inside the list, and you repeat that process again and again until you reach the last process inside the list of all the processes. And you can see that there are some other functions to get the process ID. You can get the first DNN file opened by that process, and you can get the next DNN file in the list of all the DNN file opened by that process, and you can keep calling the last function until you get all the DNN file opened by that process. So here's a full architecture again. So you can at the bottom you have framework named libdi, and libdi can give you the access to the debugging information in all those objects I showed you before. And we support Windows object and Linux object so far, and you can see that in the middle layer. And on top of that, we have the actual API that extract all those objects from the memory for you. And here's a full picture again. So eKimono run at the bottom, and it gives you the access to the physical memory and virtual memory. And eKimono provide the service to eKimono run on top of that, and eKimono can access to the physical memory and virtual memory thanks to eKimono, and eKimono can return the information about all those objects inside the memory that you want to access to. And eKimono is built on top of eKimono, and eKimono can access to all the objects inside the guest virtual machine, and it can process the information and perform any action, for example, like scanning the memory to detecting malware inside the guest virtual machine. Yeah, that's a picture. So you can see that there are some other advantages provided by eKimono. First, you can see that our scanner runs totally outside the virtual machine, and we don't need any support from the guest virtual machine. You don't need to install any agent inside the virtual machine. Just run the scanner outside, that's all. So it's very easy to deploy our scanner. And actually you can see that we have zero cost on deployment, because if you have, for example, a machine that run 100 virtual machine on that, normally you have to install 100 malware scanner inside each virtual machine. But now you don't need to do that, because you just run one scanner outside. So you have zero cost deployment advantage. Yeah, so about implementing eKimono, as I said, we use a service provided by the below framework, eKimono, and you can access to all the OS objects inside the memory. And after we have all those objects, we perform many tactics to detect malware. First one, we use a method named baseline detection. So the idea is that you create a baseline when you know that the system is clean. And after that, in the future, if you want to detect the malware inside the virtual machine, you scan the virtual machine and you compare the result with the baseline. And if you see something not in the baseline, you can report. It can be malware. So you can see that we need to define baseline for the clean system. You can have baseline about kernel module, about system code, about processes, about connection network, and something. Besides baseline detection, we have another detection method named cross-view detection. And the idea is that usually when the attacker installs the rootkit inside your system, the rootkit will try to modify your view, so you don't see the rootkit anymore. But usually the rootkit is not perfect, so if the rootkit modifies something and you don't see that anymore, but you can see that from another view, and you can still see that information. For example, there are some rootkits that try to remove one process from the list of all the processes in the memory. But if you look at the list of all the processes in the memory from different view, you can still sometimes see the different view, different result. And they call this detection method named cross-view detection. So you compare critical system object from different point of view, and if you see the difference between views, you can see that something's wrong inside the system, and it can be rooted. So far we perform cross-view detection on processes, threads, DNN, kernel modules, network connection, and the port. The third detection method we employ in eKimono is black and whitelist checking. So the blacklist detection is very simple. You know for sure that if you see something inside your system, you know that that's rootkit, that's malware. For example, some well-known malware can install some well-known kernel module inside the system. So when you see the list of all the kernel module and you see one that is well-known from malware, you can see that your system is infected, right? So basically, blacklist detection method, we list all the known bad object, and if you see something in the blacklist, you can report as malware. But you can see that sometimes we still have many false positives, so we have another checking named whitelist. So in the whitelist, you list all the exceptions that should not be reported. So you can use whitelist checking to eliminate many false positives that the malware scanner can report. And the final detection we use in eKimono is named abnormal behavior detection. So basically that the rootkit can modify your system in many places, in many critical places. For example, it can modify the import arrestable, export arrestable inside processes, inside kernel module, inside the DNN, inside they can modify system code. So the idea is that if you see the information that should not be like what it is, you can report. For example, normally the system code on the system code arrest should point to one kernel module inside the Windows. And when you check all the system code, and if you see one system code point to somewhere else, not into that kernel module, you can report, right? Because that's abnormal things. And you can do the same detection on the other type things like IDT, GDT, import arrestable, export arrestable, and many other things. And here's a detection model. You run the baseline detection first, but actually baseline detection can be optional, because in fact you don't always have baseline. So if you don't have baseline, you can ignore this step. But if you have that, you can run baseline detection, and This one can report the malware. And cross speed detection can also report malware. Behavior detection can report malware. Blacklist, whitelist detection can report malware as well. So you can perform many detection, and each detection can report malware for you. So we have many detection like that because we want to make sure that if one malware evade one detection, it can be reported by another detection method. Yeah, that's about the architecture, design, implementation of eKimono. And in the next part, we have some demo, so you can see that eKimono can really detect the malware. So we try to detect some rootkit inside user space and kernel space inside Windows virtual machine. Yeah, at first we have some screenshots here, some screenshots, so you can see that our scanner can detect malware. For example, here we try to detect a keylogger named init keylogger, and you run a scanner on the host virtual machine and scan the Windows virtual machine. And you can see that if the virtual machine is installed with this keylogger, our scanner can detect that the keylogger installed some new kernel module, which is rated on the screen. It installed 3 new kernel modules into your Windows system, and after that, this keylogger modifies 3 system code. You can see that at the bottom. It modifies anti-create key, anti-enumerate key, and anti-open key. 3 system code. The other rootkit is named Futu rootkit, and when we run the scanner on the virtual machine, you can see that when the virtual machine is infected by Futu rootkit, you can see from outside that this rootkit tries to hide one process, which is iExplorer.exe on the screen, and we detect this hidden process from performing cross-view checking. And you can see that this rootkit also installed one kernel module named msdirectx.zip into the system. Finally, there's one rootkit named Vanquish rootkit, and we perform when you run the scanner on the virtual machine. You can see that this rootkit patches many imported functions inside services.exe. You can see the red line, and it also patches many imported functions inside svhost.exe. And there are a lot more modification. It tries to patch explorer.exe, so you cannot use explorer to find the Vanquish rootkit, which is installed in the file system. Yeah, that's it. You can see that our rootkit scanner can really detect some popular rootkit, and that's not on. Here's some live demo for you. So in this demo, I show you that my scanner can detect some real rootkit, and in this demo, I run the malware scanner, the eKimono, on Zen virtual machine. And on this screen, you can see that I'm on the host virtual machine, domain 0 in Zen. And let's see which virtual machine running now. XM this. Yeah, you can see that we have 2 virtual machine, domain 0, which is a host virtual machine, and I'm inside the domain 0 now. And we have another virtual machine named XP3, which has ID 1, and it's here. This Windows XP Service Factory, latest updated. And now, let's try to run the eKimono scanner from domain 0 to scan the memory of the Windows XP virtual machine. I need to specify the virtual machine that I want to scan. And you can see that I want to scan the virtual machine which has ID 1, right? Minus X1. And after that, I need to specify the operating system type of the virtual machine, which is XP Service Factory. Now we run the scanner. Yeah, you can see that my scanner scan many things inside the Windows virtual machine. And actually, I can tell you that my virtual machine is clean now. And you can see that from the result of the eKimono. You can see that I'm trying to looking for hidden processes. Nothing wrong. I look for hidden kernel module. Nothing wrong. I look for unregistered kernel module. Nothing wrong. Check export arrest table, nothing wrong. Checking system code, nothing wrong. And checking for the IRP hook inside the Windows driver, nothing wrong. Import arrest table in the processes. I check all the processes inside the virtual machine, nothing wrong. Actually, there's something wrong. You can see here. My scanner report some place that can be patched by something in some imported function, but actually this is false positive and you just ignore it now. Okay? So from running the scanner, I can say that my system is clean. Now inside the virtual machine, I run on rootkit. Actually it's not rootkit, but it is many rootkit technique, so you can detect this program from the scanner. You can detect the real rootkit as well. And actually this time I run the famous program from the sys internet named Resist G Monitor. This one should be familiar with everybody here. So Resist G Monitor can be used to monitor all the activities inside with a resist G inside the Windows. Okay? So now from outside we run our scanner again, and let's see what it can find. You can see many red lines. Yeah, it takes a while, about 1 minute to scan everything. Now you can see Resist G Monitor installed one kernel module named rexsys701.sys inside the system. And you can see that this kernel module stay here in the file system. So you can detect that this rootkit installed one kernel module inside your virtual machine. And moreover, this rootkit patch many system code here. Anti-close, anti-create key, anti-delete key, anti-delete value key, anti-enumerate key, and so on. Resist G Monitor patches many system code. So you can see that you can really detect the rootkit, right? Now, if I close this one, I close a Resist G Monitor, so the rootkit doesn't run anymore, right? Now I try to scan again to see if now my scanner can detect something or not. Can you see that? It's very different now. You can see that if I close the Resist G Monitor, it still keeps the kernel module inside the memory. It doesn't unload the kernel module. It's still, you can still see it here. But after we close the RISC monitor, it recovers the system call table. So the system call table is not patched anymore, not infected anymore. So that's clear, right? Yeah. Okay, that's about detecting rootkit that can modify the kernel inside Windows virtual machine. Just another demo for you. This I run another program. This one is also not rootkit, but it behaves like rootkit. It uses many rootkit techniques. So if you can detect this one, you can detect the rootkit as well. Yeah, this is a program. And this program tries to monitor all the printing activities inside the virtual machine. And now, let's try to run on program. Notepad. Okay. Now we try to scan again. Now the system is infected with the rootkit. Can you see that? There's some more red lines. You can see that this rootkit installed a new kernel module here. See here. And you can know the kernel module name and where it stays in the file system. This rootkit installed a new kernel module. And besides that, you can see Notepad here. This rootkit patch many important functions inside Notepad. It patch and page about documentation and documentation, start page, create DCW, start W. All those functions about printing, so it can monitor the printing activities of Notepad. Now, let's try to close this rootkit. We unload the rootkit. And now let's try to scan again. So you can see that the results different this time as well. You can see that after we unload the rootkit from the memory, it still keeps the kernel module inside the system. It's still here. The kernel module, this rootkit is still here. But let's look at the Notepad process. Something wrong. Let me try to scan again. Okay, Notepad is here. It's not infected anymore. The imported function is not infected anymore. So after the rootkit quit, it recover those imported function inside Notepad. So Notepad process not infected by the rootkit. Yeah, that's about the demo. Okay, I don't have much time, so here come conclusion. So by running the malware scanner outside the protected virtual machine, we have some advantages. Zero cost on deployment. The rootkit cannot attack our scanner from inside, and our scanner can be visible to the malware inside the virtual machine. And from outside, you can mitigate the damage of the malware. For example, you can write into the memory of the virtual machine to disable the malware from outside. Okay. Only 1 minute left. Any question? You can see that I don't rely on the signature here. I perform 4 detection method, you can see, and I never use signature.
Can we use signature for detecting?
Yeah, it's possible. It's possible.
The object itself?
Yeah, it's possible. It's possible. And actually, that's what I plan to do in the future. But now I focus more on behavior detection. So we don't need the signature to detect malware.
How can we rely on React OS to get the address?
Rely on what?
Or we can rely to the React OS.
RealOS, they provide the code for all the objects inside Windows, processes, kernel, module.
Exactly the same?
Yeah, same, completely same. And you can verify that by checking information from the debugging symbol data from Windows. Yeah.
Will that be an issue if let's say the blue pilling of the Zen provider is from the
Detecting blue pill?
how about
No, because you can see that my malware scanner focus on detecting malware inside virtual machine. So yeah, blue pill is another thing that runs another layer, right? It's not inside the virtual machine.
But Blue who can detect your eKimono? That Blue running on your physical OS?
My scanner doesn't try to detect blue pill, right? I try to detect malware running inside virtual machine. Blue pill never run inside virtual machine.
No, I mean, Blue can detect your eKimono if they want to do it.
Yeah, but that's another thing. That's another matter. Yeah, that's another problem. Yeah.